Hi, this is Mark Rodriguez from Calsoft, and I want to welcome all of you for the webinar. We are delighted to have you join us today as we discuss logistics of change block tracking. This webinar will be hosted by Imran Khan, Architect Storage Solutions at Calsoft, and our technical panelist for today is Sriram Pore, Senior Architect at Calsoft. A quick introduction about the guys. Imran is a storage expert and has over 10 years of experience in architecting and developing products. His experience ranges not only across backup and replication, but also dedupe, CBT, SAN simulators, multipathing, file systems, link aggregation protocols, etc. We're happy to have you, Imran. Welcome.
Thanks, Mark. It's good to be here.
The introduction of our panelist, Sriram Pore is also a veteran of the storage industry and has 14 plus years of experience in developing products. He has architected, designed and implemented solutions for NAS, virtualization, integrated backup recovery and clone of VMs. We're happy to have you here, Sriram. Welcome.
Hi, nice to be here.
Thanks, guys. So before we start the presentation, I would like to go over a few housekeeping rules. We will have between a 35 to a 45-minute presentation followed by a Q&A session. By default, all the attendees will be on mute. At any time during the webinar, you can use the question window on your panel to ask any questions. If you have joined via the phone line, please mute your handset to avoid any disturbances. Also, lastly, we request you to view the session in full screen mode for a better webinar experience. So without further delay, let me hand over the platform to Imran now. Over to you, Imran.
Thanks, Mark. Welcome all. Today we are going to talk about change block tracking, why it is needed, considerations while implementing change block tracking, and some logistics around it. Recently, we have seen a lot of interest in implementing change block tracking from the storage industry. Look at VMware. VMware gave a solution vCenter Backup, which was one of the important features provided with ESX and other appliances. Now, they also provide a CBT-based solution, which helps to take quick and efficient backups of virtual machines and data stores. Now, this presentation will use some Linux terminology, but the principles are similar for any other operating system. So please bear with me. So what is change block tracking? Change block tracking or change tracking or CBT in short is nothing but making a record or journal of which blocks of a storage object were changed by I/O. A storage object is any logical contiguous space used for storage of data. For example, we have files, we have raw devices, LVMs, virtual machine disks, Windows volumes, in even RAID volumes, they are all storage objects. In the context of today's presentation, CBT does not keep track of what data was written. It only logs or tracks which areas of the storage object were written to. Such kind of tracking data is used by various applications, primarily by backup and restore. Other solutions that can use CBT are out-of-band deduplication and archival, etc. Usually, such tracking is only performed to know what blocks have changed between a given time interval. When we compare traditional backup solutions and CBT-based ones, one question does come to mind. CBT does not record data, so any backup solution using CBT still needs to use snapshots. So what is the gain if both types of solutions use snapshots? The one traditional backup and the one that is using CBT. It's a fact that traditional backup solutions rely on snapshot technologies to take backup. Snapshots are nothing but point-in-time copies of any given storage object, and these help in making the backups consistent while continuous I/O is being performed on them. However, it is very tedious to take backups of the entire object at every backup cycle. So what do? We use either incremental or differential snapshots. These snapshots tell us what has changed between two backup cycles. Let's take an example of backup using a snapshot. Now this is something that most of the storage industry is already familiar with. Here we assume a block device that is capable of snapshots. In the diagram we see a device, DevSDA, mostly this is a Linux based device. At the first backup cycle, we take a snapshot of the device and take a full backup. We attach a small area that acts as a delta area for the snapshot. This is same for whatever type of backup is being implemented here. At the next backup cycle, we take an incremental snapshot of the device. Then we calculate what has changed between the two snapshots and take the backup of only those areas. This change is determined by generating a difference of both the snapshots. In the diagram it is shown as snap1 minus snap0. Going on, in the next backup cycle, we take another incremental snapshot of the device, and this cycle is repeated every time a backup needs to be taken. There are some fundamental points that can be noticed here. One, the snapshots have to exist not just for the period of backup, but for over 2 backup cycles. It may even require to exist for more than 2 backup cycles. Point number 2 is that production I/O has to go through the snapshot logic when the backup is being taken, which means when the backup is in play, every I/O that comes from the application may translate to more than one read and write based on what type of snapshot it is. Point number 3, since snapshots have to live for a longer time, the size of the snapshots will keep growing, and deleting these snapshots will become tedious. The effect of points 2 and 3 is multiplied when the backup interval is large. Imagine that the backup interval for any data center is 1 week. Deleting a snapshot in case of redirect on write type would mean merging entire week's worth of data onto the base object. All these points degrade the performance of production systems. No matter which snapshot logic is used, snapshots impact performance in one or the other area. This table gives you a small comparison of redirect on write type of snapshot versus copy on write. As you can see, time to restore snapshots is very high for copy on write types, whereas in case of redirect on write, deleting snapshots is very costly. This is the problem that change block tracking is trying to solve. And how does it do that? Change block tracking keeps continuous track of what blocks have changed between given time intervals. Backup applications need not rely on snapshots to know what have changed. They only use snapshots to get the point-in-time copies. Other than that, any tracking information, they get it from the change block tracking module. Hence, there is no more need to keep the snapshots alive after the backup is complete. To take a backup, one needs to essentially know what has changed between 2 snapshots. For this to happen, as soon as a snapshot is taken, any new I/Os are attributed to the next backup cycle or snapshot, meaning a new tracking instance has to be started atomically with the creation of snapshot. However, changing or integrating with the existing snapshot technologies is very difficult and something that is frankly not necessary. This problem is easily solved by using 2 tracking instances overlapping across the snapshot creation operation. Let's take a look at how this is going to work. The bar that you see here represents the timeline of events. As I mentioned earlier, snapshot creation and start of tracking instance should be atomic to not lose any tracking information. But here we start the tracking instance and then take a snapshot. There is a time lag between these 2 operations, but we'll come to that later. This is followed up by a full backup. Here what we do is we use the tracking instance, but we do not use the tracking instance but take the backup of the entire base device, since this is the first time that the backup is being taken. Once the backup is done, we delete the snapshot. Change block tracking module is tracking the changes, so we do not need the snapshot anymore. We then follow it up in the next backup cycle. We start another tracking instance, which is represented here in the diagram by TI1, and then follow it up with another snapshot. Then we stop the previous tracking instance, TI0. Now TI0 contains all the blocks or information of all the blocks that has changed between snapshot 0 and snapshot 1. We take a backup using snapshot S1's base and the information provided by tracking instance T10. This will essentially only be an incremental backup. It will be similar to an incremental backup taken using an incremental snapshot. After the backup is complete, the snapshot is no more needed and can be deleted. This cycle is repeated at every backup interval. As you can see, the lifetime of the tracking instances T10 and TI1 overlap for a certain period of time. This is to overcome the atomicity problem with the snapshots. Even though it looks like TI1 have recorded more blocks than the snapshot, it is okay. At the end, we are only taking the block addresses from the tracking instance and copying the blocks of the snapshot. So we only end up copying extra blocks that have not been changed. We have seen in the previous slide that we stop tracking instance before we take a backup. So the question arises, what do we do when backup fails? Using two tracking instances, that problem is also solved. This is the flow chart of the timeline we saw in the earlier slide. First, we start tracking instance of a particular storage object. Then we take snapshot S0. Then we take a full backup using the base device of the snapshot. After the backup is complete, we delete the snapshot. At the next backup cycle, we start a second instance of tracking. We take another snapshot of the storage object. Also, we stop tracking the previous instance. Using the previous tracking instance, we can take an incremental backup. In case of a successful backup, the iteration looks something like this. What happens in case of the failure of the backup? In this case, we can start another tracking instance x+1 and we take another snapshot. We follow it up by stopping the earlier tracking instance of tracking instance x. Then we take a backup, but instead of using the earlier tracking instance, we merge the previous two tracking instances x and x-1 and we apply the change tracking information given by the merged bitmap to our backup. This merge gives us appropriate changes that pan over the failed backup timeline. Implementation of CBT will differ according to the storage objects and the operating systems for which they are designed. However, few principles and components will remain same. Most important component of CBT is the hook or the filter. This hook basically allows you to take a peek at the I/O on the storage object and record it. Obviously, we will only be recording the metadata of the I/O and not the data. The most important requirement for the hook is that it has to be fast. Since the problem we are trying to solve is to lessen the delay of production I/O during snapshot, the same needs to hold true here. Also, the hook does not need to care whether I/O itself is successful or not. In this case, I/O has failed, that particular block will be recorded by CBT. This will result in unchanged blocks being backed up, which does not make the backup inconsistent. One would think that a hook should be in the I/O path and therefore should be in the kernel, but it is always not the case. A hook redirects the I/O path of the storage object being tracked. If the storage object itself is managed in the user space, the hook can also be present in the user space. One good example of this case is the user space file system. For example, NFS Ganesha. If you are taking backup of the files exported via NFS Ganesha, we can hook into the I/O path in the user space daemon itself. In Linux, there are many ways that an I/O path can be hooked for various storage objects. RAPFS, for example, can be used to stack on top of any existing file system and hook into the file I/O path in the kernel. It is similar to something like a Windows Miniport driver. Modules that use JProbes and device mapper targets can also be written in Linux to hook into the block IO path. One can also create custom hooks for block devices in Linux, like redirecting the make request function of any block device to custom code. These are some of the points to be taken into consideration while designing the hook module of any CBT software. A hook can either be static, meaning once it is inserted, it may not be possible to remove it on demand. An example of this scenario is a stackable file system. This kind of hook cannot be removed if there are open file handles that use the hook IO path. On the other hand, dynamic hooks can be implemented that can be removed on demand. If a storage object is not being tracked anymore, that particular hook can be removed from the IO path. Device mapper targets are a good example of this kind. While adding or removing a hook, the IO to that particular storage object may need to be suspended. This may degrade performance of production IO. This also contributes to the earlier decision of whether the hook has to be static or dynamic. It may be costly to keep adding removing hooks than keeping the hook in the IO path and ignore the tracking data. Time spent in the hook should also be minimal. As mentioned earlier, this solution is to overcome the performance degradation problem of snapshot-based backup. So the module that records the IO or the metadata of IO should be very less time consuming. Storage object can be a volume or a partition of the volume. Sometimes hook will redirect IO of the entire volume, out of which we might only be interested in the IO that is being done to one single partition. This is the granularity of the hook. IO of the entire volume may be delayed even if only a partition is being tracked. Last but not the least, one important thing to make sure is the hook module tracks each and every IO path to the storage object. Sometimes some applications like Oracle or some databases, they bypass the usual IO path and do direct IO to the block device. If any such IOs are missed, then the corresponding backup will be inconsistent. Some storage objects are available for access at very early stage of the boot sequence. For example, bootable SCSI devices. If such storage objects are to be tracked, then the hook has to be in place before any such access is performed. Similar to the earlier point, if this is not taken care of, the resultant backup will be inconsistent. Change area cache is another component which may not be implemented based on design. This is a temporary holder of the change metadata. This metadata is held here until it is flushed to persistent record. This is needed to make the hook very fast. When the hook is in place, the IO is redirected to this module and is recorded in the entry cache before it is flushed down to persistent record. The size of cache is an important design principle for good performance. It's a simple producer-consumer problem. The size of the cache is dictated by the rate of IO metadata produced and the rate at which applications consume it. The cache can be static or dynamically growing, or it can be assigned per storage object that is being tracked. These are all implementation or design decisions that need to be taken care of for performance. The entry cache can be in user or kernel space. In any case, the user space or application needs to access it. In Linux, the various methods available for this purpose are memory maps, direct copy to user, or netlink sockets. I am sure that Windows has its own method for kernel to user data transfer. Persistent records is another important component of change block tracking. The format of persistent record should be such that it is easily consumable. One can use a log structured record where the tracking data is just appended to the end of the file. However, it may result in more post-processing. VMware probably uses one such structure to keep its tracking data. Another type is the bitmap, where every bit represents a logical extent of the storage object. The bit is set if the logical extent is partially or fully written. This avoids having a large bitmap. Multiple bitmaps can represent multiple tracking instances. The bitmap is relatively easier to consume, and operations like merging of bitmaps can also be performed easily. A log structured file may run out of space. Similarly, a bitmap size is dependent on the logical extent represented by a bit. This is the granularity of persistent record. Since backup intervals may be large, the records need to persist for a large time. So the granularity of the record needs to be a very optimal value. As mentioned earlier, it is very possible that the hook module is loaded at the very early stage of boot. It is also very much possible that at that time, there is no access to the persistent record. During shutdown sequence, it is possible that the device that the bitmap lies on is not accessible anymore. Such things need to be taken care of while designing the change block tracking module. The changes in the entry cache may be flushed to the persistent record asynchronously. However, this delay may affect the backup cycle and needs to be taken care of during design itself. I've already talked about the various types of persistent record and their uses, log structured versus bitmap. One also needs to keep track of the number of persistent records that are being stored and their generation numbers. This is to take care of the space that is being used to store the persistent records. Let's talk about how an application may, it be backup or anything else, consume the CBT information. There will be a server running at the location of the CBT instance and act as an interface into the CBT software. It will provide a set of APIs that can be called upon by the application to control the CBT actions. This particular server or the APIs can be called upon locally or remotely. While if this server provides APIs that can be called remotely, we have to take into consideration the network congestion as well as data transfer over network. The server also needs to uniquely identify the trackable objects. This unique identification is very important because the objects need to be identified uniquely across machines and probably worldwide. It depends on the data center where change block tracking is being deployed. Since most of the change block tracking information is in binary and is going to be sent over the network, we should have some sort of base64 encoding or another form of ASCII encoding to make sure that the data is consistently transferred over network. The APIs have to be portable to interact with multiple backup applications and software. The API should also provide support for clustering. Now, a storage object may also be a clustered volume. So when it is being tracked and if the volume fails over to your secondary node, then you need to make sure that the tracking information also fails over or some notification is being transferred to the tracking module or software to let it know that the cluster volume has failed over. This needs to be considered very delicately because during failover it might be the case that the change tracking is not able to insert the hook in place and the IO that is being tracked may result in an inconsistent backup later on. Some examples of the change block tracking APIs are list trackable objects. You can either start tracking a particular object or stop tracking it. You can also force it to sync all the information that is there in the entry cache to the persistent record. You can stop tracking an entire object as compared to the partition that is present in it. You can list the currently tracked objects. You can also list and get the persistent records that are attributed to the storage object that is being tracked. You can also delete or merge the bitmaps. You can get some bookkeeping information. Let's talk about some of the scenarios that come into play when change block tracking is implemented. Reboot support. As I've talked earlier, if we are tracking a device that is available for access at very early stage in boot, you will need the change block tracking driver or the solution or the hook to be in place before that particular volume is allowed access from the applications. This is very important for the backups to be consistent. Not just during boot, but also during shutdown. It is very much possible that the applications do some I/O at the very end of the shutdown sequence. So we need to take care of such sequences if we are tracking a device that is available at boot and shutdown. Cluster support, as I have already talked, is one important consideration when CBT is in play. In Linux, it is very much possible for devices to go offline. For example, if you have an iSCSI target connected to the initiator, it is very much possible that the target puts the device in offline mode, or due to network congestion or in the switch network, due to some error, that particular device on the initiator is in offline state. When the device comes back online, it is also possible that Linux attaches it to a different kernel object. So the CBT solution needs to take care of such kind of situations. I have iterated in this presentation. The change block tracking logic is mostly to overcome the performance degradation problem that is brought on by snapshots in the data centers and production I/O. So any part of the CBT module should take care of performance. It should not delay the I/O any more than the snapshot do in the normal case. Stress testing for such a solution is a must. You might want to upgrade your CBT solutions, and depending on if the hook is static or dynamic, you would want to dynamically upgrade the hook to point to your new modules. It is very much possible that I/O needs to be suspended during upgrade. This downtime needs to be taken care of during upgrade. So we have talked about the what, the why, and the how of CBT in this presentation.
All right, thanks Imran. As Imran just said, now we will be discussing any questions you may have regarding the webinar. If anyone has any questions, please type them in your questions window in the panel on your screen. We're going to give you a couple of minutes for that. Can you help understand what do you mean by cluster support?
Okay. So a cluster volume is seen as two separate devices on two separate instances of the operating system. So if you are running a CBT solution on one and not running a CBT solution on another, if the cluster volume fails over, or even in case of an active cluster volume, it is the changes that are being recorded by only one side will become inconsistent if the backup is taken. Similarly, you may also need to fail over the CBT service or the CBT server or the CBT solution itself along with the cluster volume to the other node when the cluster volume fails over. This guarantees the consistency of the I/O or the tracking that is performed on that particular cluster volume. I hope that answers the question.
I think it does, Imran. So we seem to have had a technical issue, Imran. We're going to quickly run through the first couple of questions that we had. You could recap those. So for all our listeners, the questions that had come out in the start were, can you share some light on what all needs to be considered to calculate the typical memory requirements for tracking the changes, that is log structured over bitmap?
So for the memory requirements, I've already mentioned that there is two components, that is the change area cache and the persistent record. For the change area cache, depending on the design, it can be an in-memory cache, and the size of that particular cache or the memory requirements is dictated by the IOPS or the IO per second of the system under test. Now, the change area cache can record the size and the offset of the particular IO to a storage object. So the size of the entry cache should be the worst possible IOPS that the system can be loaded with. Similarly, for the persistent record, they are stored on disk. For example, a log structured file or a bitmap. For a log structured file, the size of the file is dictated by the amount of disk space that you have left. Since you are appending the entries to the end of the log, it may become a pretty huge file. You need to make sure that at every backup cycle, after the backup is complete, you delete the particular log structured persistent record associated with it. For bitmaps, you need to have an optimal grain size. Now, grain size is the size of the logical extent of the track object that is represented by a bit. Depending on the size of the device, the size of the bitmap is calculated, and it will remain consistent or constant across reboot. You need to make sure that this value is optimal to achieve an optimal bitmap size. Also, you can use something like a sparse file so that unused bits are not allocated on disk, and there you can save some space while persisting the track changes.
How should or would CBT behave in case the system that is being tracked crashes?
Right. So in case that the system crashes, you would lose all the tracking information that is in the entry cache. It is also possible that if you are having a persistent entry cache during a system crash, there is no guarantee that you have recorded all the IOs that have gone through to the device. So it is recommended that you start with a full backup cycle and start using CBT anew.
All right, and the last question that we are taking for today, Imran, what are the various points to be considered to support zero downtime even in case of support for upgrade of CBT, the additional enhanced functionalities, non-disruptable upgrade?
Well, technically speaking, zero downtime is very hard to achieve in case of kernel module. You would mostly need to suspend IO for a very small time where you are placing in the hook or removing the hook. But it is very much possible that if you keep the hook module as a separate entity and you do not change the entry points to that particular hook, you can keep the hook loaded and you can have a separate module that interacts with that hook to record IO. And you only need to upgrade the recording module and not change the entry hook. Such a solution is possible in Linux as well as in Windows, I think.
Okay, brilliant. Thanks, Imran. So that ends our webinar for today. If there are any further questions our listeners may have, you can write to us at marketing@calsoftinc.com and we will strive to get those questions answered. Well, thank you, Imran, and thank you everyone for taking the time to join us today. We hope you found this session valuable. As we said, we'd appreciate any feedback that you may have for us. And the email address is marketing@calsoftinc.com. For our listeners, please look out for our email with the webcast recording and the presentation. Goodbye and have a great day.
Thanks, Mark. Have a nice day, guys.
Thank you. Bye-bye.